Okay, so let's call this section basic rules for evaluating the efficiency of a given algorithm. So now we have got the theoretical foundation. Now, how basically we're going to approach given any algorithm. So rule number one is for loops. So when you see for loops, the running time, so T of n of a for loop is going to be at most the running time of the statements inside the for loop times the number of iterations, right? So if you have an algorithm where you're writing int I equal to 0, I less than n plus plus I, and then you have a bunch of statements s1, s2, and so on and so forth, right? So whatever is the cost of this guy, right? This total cost of all these statements multiplied by the iteration count, that's going to give you the overall runtime. So therefore, if you find you have a regular for loop and you have a bunch of statements, so if you just have statements, they typically are considered to be constant time, right? Unless they are also carrying some compound statements like having nested for loops. Otherwise, they are all constant time. So effectively, when you see a for loop which is running n times, and then you have just bunch of statements, they are all considered to be constant time, and therefore the complexity of this is going to be big theta of n. It's as simple as that. Rule number two, please feel free to interrupt me if anything is not clear, okay? Nested loops. So nested loop situation is going to be, you have a for loop. Nested loop situation is, you have a for loop running for, let's say, n times, then another for loop inside, which is running for m times, another for loop inside, which is running for p times, and then you have a bunch of statements here, right? So then what is going to be the complexity here? How would you evaluate the complexity? It's going to be the multiplication.
N cubed times whatever is inside.
Can you repeat that again? What? Can you say that again?
I said n cubed times whatever is inside. N cubed.
Yeah, so here this is running n times, this is running m times, this is running p times, right? So it's going to be n times m times p. Of course, if all of them are, you're right, like all of them are running n times, then it's basically a cubic algorithm. Do you remember what I said last time? When the algorithm becomes totally useless, beyond what point?
You said two for loops.
Correct. So anything beyond n log n, or when the algorithm is quadratic and above, right? Then pretty much the algorithm is useless for large values of n. So this would be an example of a practically useless algorithm. Okay. Rule number 3 would be consecutive statements. So if you have a for loop running n times, right? And then another for loop running n times, another for loop running n times inside. So what would be the way to calculate the running time here? You would be dividing into blocks, right? So it's going to be sum of this plus this, right? So this is running big theta of n, correct? This is running big theta of n square. So consecutive statements you add. So consecutive statements become additive in terms of cost. So therefore, it's going to be big theta of n square plus n. And you look at the what is the highest order here? N square. So this is going to be big theta of n square. Is that clear? Okay. Rule number 4. When you're encountering if else, the conditional sections of the code. So if you have if some condition and then some statement, else s2 some statements. So what do you think in this case we should be doing? Any ideas?
Is it n because it will never be the case that both the if and the else run?
Yeah, so you can basically, if this turns out to be like this S1, this whole region turns out to be big theta of n square. If this turns out to be the big theta of n, right? So either you can say it's a max of both, or it doesn't matter if you add it. So n square plus n, that would be equal to big theta of n square. Because this is going to anyways dominate. So therefore, there's no harm in this also being additive. So all the mutually exclusive section can be additive and you still would not have any problem reaching an appropriate bound. Question? Is it clear? Okay. Now the 5th rule that I'm going to share today, this is going to be probably the most interesting one. When you have a recursive algorithm. So in the case of recursive algorithm, your running time function is also going to be recursive. And therefore, you need to be able to solve such a recurrent relationship. So in order to better appreciate that, let me just introduce a new search algorithm called binary search. Now, you all would have already might have heard about what is binary search. So here is the problem. So I'm going to come back to how to actually evaluate the cost function, or the how to solve a recurrent equation. So in this case, recursive algorithm would mean there will be recurrence relationship in the expression for t of n. So I'm going to come back to it, how we're going to solve it. But first, let me just introduce a new search algorithm, and then we'll try to evaluate the cost of that algorithm. Okay. So what is the problem here? So the problem here is that given a sorted array, so given a sorted, okay, it's important that this is a sorted array. So for example, can be a dictionary. So given a sorted array, search for a value, let's say a val. Okay, so this is what you're looking up. Okay, so if we find a val, then return the array index. Otherwise, return -1, because -1 is not a valid index. Okay, so if I take an example, let's say -8, -7, 0, 0, 2, 7, 7. Suppose this is the sorted sequence. Okay, and you're looking for 2 in this. What is the basic approach that you can take? If suppose this is your array, what is the most basic approach you can take to look up for 2? What is the obvious method?
Regular for loop, iterative search.
Exactly. So walk through the list. That's it. And you keep looking wherever you find the match. That's it. But just imagine if I ask you to look up for a word in a dictionary, is that how you look up? So if I
No,
ask,
you go to the letter.
huh? Say that again?
You go to the letter it starts with.
Yeah, I mean, you would not actually go page by page. If I ask you to look for a word xanthosis, okay? Ask you to look up for this word. Would you be going first page, then second page, then third page, then fourth page? You can see this, right? So this searching for an item in the sorted array is almost like that. That when the dictionary is given to you, you're going page by page by page. You can see how inefficient it would be, correct? That does not make sense, right? So in fact, the approach of the binary search pretty much follows what we practically do when we are looking for a word in the dictionary. So we would arbitrarily just open the page, right, approximately towards the end, because when I see that, okay, it starts with X, why bother opening the dictionary somewhere in the first middle, in the first half of the dictionary? Most likely you're going to look at the second half, correct? Knowing that it starts with X. And after you have looked, you're going to jump around further. And that's exactly what this does. So here, binary search would do what? It would split into half. So it would first find the middle term. So how many terms are here? 1, 2, 3, 4, 5, 6, 7, right? So 7 divided by 2 is 3. So 0, 1, 2, 3. So this is the middle term. And then you compare the middle one with 2. Is 2 greater than or less than? So you find that the 2 is greater than. So therefore, there is no point in looking on the left side of this middle item, right? So our focus goes here then. So now when we look here, there are 3 items. So out of the 3, you again look for the middle. So there are 3 elements. So 3 divided by 2 is 1. So 0, 1. So your next item comes here. So it's 7, right? So now 2 is less than 7. So then you go to the left. And now you're left with only item 2. And you nail it down. Right? Okay. So now with this intuition that we developed right now, let's apply the technique that we learned for divide and conquer in the context of recursion here as well, right? So if you have to write a binary search algorithm, how are we going to write it? So you are given an array A, okay? The leftmost index, let's call it left. The rightmost index, let's call it right. So this is acting as the A with left to right. Okay, that's the range in which all the elements are residing, right? So the first thing, what is the first thing that we try to do when we are applying a recursive style? What is the first thing? Do you remember? We look for what? Arguments, right? What should be the arguments? So what are the arguments here? Can you suggest what are the arguments that you would give to a binary search algorithm?
Maybe the array itself and its length.
So you will be having A, right? You will be giving the index at the leftmost position and the index at the rightmost position. And what else? The value that we are looking for, right? So a val, that's what we are looking for. Pretty much that's what you would come up with as arguments. And then we write the base case, right? So what is the base case here? So there are two base cases one can think of, right? One base case corresponds to when it is not found, another base case corresponding to when it is found, correct? So what do you do? When do you conclude that you did not find it? Suppose I was looking for not 2 but 3 here in this. What would have happened when I have come here? We find here that the 3 is less than 7. Then I come here, right? So here left and right both would be equal to 0, right? There is only one element, right? So left and right value will be 0. And then what do we do when it is 0? You try to find the midpoint, right? And the midpoint happens to be this. So somehow or other, if we are looking for a value which is out of range, after searching, you end up in an out of range for the indices. That means you did not find it. So one exit condition that can happen is that the left becomes greater than right while you're searching, and then the output will be equal to -1. This is the first base case. The second base case is when you're able to find it. So when are you able to find it? When the midpoint is equal to left plus right. So this is the not midpoint but the mid index of the mid element. So that's going to be left plus right divided by 2. So when you find that A of val is equal to A of mid, right? So then this serving as the exit condition in a positive way, where out is equal to returning the index of the position that is found. So out equal to mid. And the inductive step, or
sorry to interrupt you.
go
Could
ahead.
you repeat the first base case explanation again?
Sure. I think let me come back to it. It will become more clear when I discuss the recursion, okay? I'll come back to this so that it will become easier for you to follow. So when are we actually recursing? When we find, like you saw, there are two places when we are just moving around. One was the case when the a val was less than the midpoint value. So a val was less than a mid, right? So when it was less than, where should we be looking for? We should be looking for in this range. So what is this range exactly? So this is our mid, right? This is left. This point is left, right? So this point is then what? It is mid minus 1, right? And what is this on the right hand side? If it is greater than, then we are looking up from mid plus 1. So this is representing mid plus 1, right? And this one is representing right? So that's where we are looking for, correct? So if on the left hand side we have to go, then we would be writing out is equal to b search. Okay, what would be the argument? So a will come straight because it's the same array, but the range has now changed because I'm looking in the left side. So left side would mean left to mid minus 1, right? So it would be left to mid minus 1 and passing in the value I'm looking for, which is a val, correct? And the other condition for recursion is a val is greater than a mid, in which case my out is going to be equal to what? B search of a, then what is the range we are putting here on the right hand side? What should be the range here? You want to look here?
Mid plus 1 to right.
Exactly. So mid plus 1 to right and a val, right? Okay. Now let's look here. When it came to this point, right, there were three elements, right? 0, 1, 2, right? 0, 1, 2. Here left was equal to 0, right was equal to 2, and mid was equal to 1, right? When I did not find it, right, then the new range became what? Suppose I was looking for 3 instead of 2, right? So I was looking on the left hand side of the mid, right? So mid minus 1 is, so 1 minus 1 is 0, right? Correct. So left is 0 and mid minus 1 is also 0. So it is looking in the range of 0 to 0. So left equal to 0, right equal to 0 when it is looking, right? And it is again taking an average. Okay. What is the average it took? 0 plus 0 divided by 2, which is 0, correct? At this step.
Sorry, where does a 0 come from? Is that like the truth value or something?
Hold on. Let's be clear. Are you with me here? Like when left is equal to 0, mid is equal to 1, and right equal to 2 when it was looking at this spot?
Mm-hmm.
Is that clear?
Yeah.
After this step. So after this step, let's say we are looking for not 2, but we are looking for, let's say 3. So let's say we are looking for 3 at this step. So what are we going to do here? The midpoint is 7. So we are looking for 3 here. So because 3 is less than 7, we are going to look on the left hand side. So then my left will be equal to 0. Right would be is equal to mid minus 1, correct? Because I'm looking on the left hand side. So 1 minus 1 will be 0, correct? And now the new mid will be left plus right divided by 2, right? Which is also 0, correct?
Wait, isn't the right mid +1? I thought that's what you said.
So let's be clear. When we are finding that it is less than mid, right? We are here.
Mhm.
We are not here. We are here. So it is left at mid -1. So left is 0. Left is 0. Mid -1 also becomes 0, correct? Because mid was 1.
Mhm.
The mid -1 will become 0, correct? So therefore the new value of left and right, when this recursion kicks in, right? The new value of left and right will become 0 and 0, correct? And then you will compute again the value of mid, which is left plus right divided by 2, which is going to be 0 because left and right both are 0, correct? Now at this point you're going to look for a match. You're going to see whether a val matches a of mid. But what is a of mid here? So a of mid is a of 0. There's only one element at this point, right? It didn't match. So 2 is not equal to 3, right? When you're looking for 3, this 2 is not going to match. When it didn't match, then what is the next step? When it didn't match, you see whether 3 is greater than 2 or less than 2. So in this case, it is greater than 2, and therefore it's going to look in the right side. So now at this point, it's going to do what? Mid +1 to right, right? So mid +1. So now at this point, it will go in this direction because 3 is greater than 2. So mid +1, so left, new left will become, so left will become equal to mid +1, which is 1, like mid was 0, and right would be become equal to 0 because there is no change in the right, right? Right remains the same. So what has happened now? The left has become greater than right. This is the condition. That's what you were asking. So when left is greater than right, then we could not find a val. So therefore, we have to return -1. Is that clear? You were asking me to explain the first condition, so I thought of explaining through this example.
So at the edge, you're saying it basically tries to look for the right again, but it's out of index because the left is the rightmost element. So like,
Because you
therefore,
incremented, because you incremented the value of left, right? Because you are looking on the right hand side, but there is nothing to look for.
Mhm.
And therefore you end up going out of range. So left becomes greater than right, and that becomes the exit. So this is the fail condition of base case, and this is the pass condition of pass exit conditions. There are two kinds of exit conditions when it comes to binary search. One is corresponding to the fail, another is corresponding to the pass. So with this, I think we are ready for writing the algorithm for binary search at this point. So let's write the algorithm for binary search. So the signature for binary search would be int b search. So int star a, right? Int left, int right, and int eval. So what is the first thing we should be doing? We should apply the base condition. So what is that? If left is greater than right, then return -1. So if left is greater than right, then return -1. That's the first base condition. Okay. If not, what are we supposed to do? We are supposed to evaluate the mid. So mid is equal to left plus right divided by 2. And now that now brings us to the second base condition. What is that? We are looking for a match, right? So if a val is equal to a of mid, which means, so this is the second base condition. Then I know that I found it. Let's put the braces, it makes it easier to read. So this is the found case. So this is the base condition number 1. So if you found it, then you return what? Here we are returning mid, because you see out equal to mid, that's the return value. So this is the second base condition, so base number 2. Okay, now the rest is just recursion. So you will come here if you did not return, so you don't even have to write an else block here. You straight away ask if at this point there are only 2 possible conditions remaining, either greater or less. So if a val happens to be less than a mid, then what you should be doing? Less than, then you should be recursing. So this is what it should be returning. So out is meaning you're returning. So return b search passing a and then left to mid -1 and passing in the a val, which is what we have to search. Else there is no other condition remaining, so we don't have to explicitly check whether it is greater than, because no other possibility exists. The equality has been checked, less than has been checked. The only possibility remains is a val is greater than a mid, in which case you do return b search passing in a mid +1 to right, passing in a val, which is meant to be searched. And that's about it. You covered all possibilities, exactly following how we have laid down the base condition, recursive condition, and the arguments. Okay, so now we are in a stage to find out the time complexity of this algorithm. Remember, when it comes to recursion, it will end up being a recurrence relationship in the time complexity equation. So
Just to clarify one thing, sorry, sorry to interrupt you.
Go ahead, no problem.
So when we cut the array into these smaller pieces, right, like we saw in the example above, so it reassigns the index value in relation to mid, is that correct? So like it becomes 0, 1, 2 in relation to the midpoint. So for example, like the right side, right?
Mm-hmm.
For the 277. So when you recurse and call that, so 7 becomes, or 2 becomes a new 0 index for that recursive call, right?
That's correct.
Well, that's not to say that it's a separate, like, that's not to say that it's kind of like copying a new array or anything, right?
No. This is relative, you have to understand. So thank you for asking the question. So let's, if you want to properly see this, so 0, 1, 2, 3, 4, 5, 6, 7, right? Let's understand this carefully. So index values were 0, 1. Thank you for asking that question, okay? Because I was trying to 5, 6, 7, right? Oh, I'm sorry. It will be 6. There are 7 elements only, correct?
Mm-hmm.
So let's see how it is. And you're looking for 2 here, right? The value of this, the A is essentially -8, -7. So A is -8, -7, 0, 0, 2, 7, 7. So first time when you are passing, the value that is passed is B search A with a 0 and right is 6, correct? Passing in the value of 2, which you are searching for. This is your A val. Next, we find that in this range, the next it's going to look on the right hand side, right? So it became B search A. So what was the 0 plus 6 divided by 2, which is 3, correct? So 3, so we are looking for 4 to 6, in the range of 4 to 6, because it has to look in the A only, right? So it cannot change it to anything else. Then we looked for B search. We found that the midpoint is 5, correct? And then it is calling on 4 to 4, 5 minus 1, right? Looking for 2. Then in this case it found it, right? Then when we change the example to, let's say, a val equal to 3, just to kind of also, so in this case it found it, correct? Because 4 plus 4 divided by 2 is 4, right? And the fourth element is 2, right? So it found it. But if I'm looking for 3, then what happens is that the search continues. And because 2 is greater, so then it becomes 4 gets incremented. So it becomes 5. And the right hand side remains the same. So now at this point, we are seeing that the left is greater than right. So therefore, this is not found. Or minus 1 gets returned. In this case, a 4 gets returned. Is that clear?
Yeah, that makes a lot more sense. Thank you.
Okay, good. Okay, so next we want to analyze what is the time complexity of this algorithm. So remember the rules. The rules are first, like the sequentiality. What are the operations happening here? No loops, right? So this is order of 1. This, there is no loop, order of 1. There is no loop here either, just some check for condition. It's order of 1, okay? But interesting things start happening here when the value is less than mid. This is what? So if the overall complexity of running this is T of n, right? This is running over what? Half of the element, right? This is T of n by 2, correct? And remember, if then else, because we are adding them up, remember? We said that was rule number 4, okay? We are adding them up. So this becomes T of n by 2. So what is the overall complexity then? T of n by 2 plus T of n by 2 plus order of 1 plus order of 1 plus order of 1. But whenever you're adding all these order of 1, it becomes order of 1, right? So therefore, what is the overall equation now? T of n is equal to T of n by 2 plus T of n by 2. So this is the if and the else part plus order of 1, which is kind of the conglomerate of all the order of 1s together. So overall, the equation therefore is T of n equal to 2 times T of n by 2 plus order of 1. So typically in the recursive algorithm, there will be some function of the T of n based on how you made the split, plus there will be this constant or some kind of extra values that will come in, whether it is going to be order of 1 or order of n or order of n squared. That depends on what else is happening in the base conditions or in the non-recursive portion of your algorithm. So this captures the non-recursive portion, and this captures the recursive portion of your algorithm. That would be the typical way in which the recurrence relationship will come out. So what's the step that we can take here? So this is going to be what? 2 times We're going to expand this. How do we expand? We know T of n is 2 times T of n by 2 plus order of 1. So we know what to write then. We just substitute. So n with n by 2, right? So n by 2 divided by 2. So that becomes n by 2 square plus order of 1, right? All I did here at this step, it just expanded this guy based on this equation that we wrote. I just expanded this. I just substituted n for n by 2, right? So therefore it became n by 2 divided by 2. So therefore it's n by 2 square, and it was 2 times. So that 2 times comes here plus order of 1. Please feel free to interrupt me because this is a very, very important step I'm showing. Plus order of 1. This is essentially this particular one. All I have done at this step is just expanded this. So this makes it 2 square times T of n by 2 square plus order of 1. Okay, what's the next step? Same thing. I can do one more time. I can go 2 times T of n by 2 cube plus order of 1 plus order of 1. So here at this step, I have expanded this guy, but I forgot to put order of 1 here, which corresponds to this. So this is going to be order of 1 plus order of 1, right? So you had order of 1 plus order of 1, and there is going to be this particular term gets replaced with this plus order of 1. So this guy is this, and then this guy is here. Okay. So what did we get here? 2 to the power 3 times T by n by 2 cube plus order of 1 plus order of 1 plus order of 1. You're almost seeing a pattern here. The number of times order of 1 is repeated is 3 times here. This is 2 to the power 3. This is n by 2 to the power 3. You almost see a pattern. So we can generalize it that it can keep going like this. I can just replace 3 with k. So it will be 2 to the power k T of n by 2 to the power k, right? I'm just replacing 3 with k by just generalizing it, plus order of 1 plus order of 1 plus dot 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 plus order of 1. How many times is this going to be repeated based on this? K times, right? Wherever you see 3, pretty much it becomes k. So what does this mean? This means 2 to the power k times n by 2 to the power k plus k, because it's 1 plus 1 plus 1 plus k times, so that becomes k. Or if you like, you can even put this theta notation. That's fine. Okay, so now where do we go from here? So one thing that you can see is that at every step we are dividing by 2, right? So this particular term is becoming smaller and smaller, right? At every step, correct? But there is something that we already know. What is that we know of? We know the exit condition. When the number of terms here is equal to 1, what will be the complexity of this? It's going to be order of 1, right? When you have only one element. So we know that T of 1 is equal to 1. So this is very important factor. So T of 1 is theta of 1. So this is going to help us solve this recurrence relationship. So typically, when we are solving the recurrence relationship, just this is not sufficient. You also need to know what is the exit conditions timing. So T of 1, we know in this case is theta of 1, which we can see here. If the value of left and right is matching, we know that it's going to straight away exit from here or exit from here in just constant number of steps. Okay, so having known that, then one obvious way we can end this recursion is, because this guy is becoming smaller and smaller, when is going to when would it be favorable for us to end this? When I can make this T of 1, right? Because I know the value of T of 1. So I would like this term to become T of 1 by becoming smaller and smaller. How can this become T of 1? This can become T of 1 if n by 2 to the power k is equal to 1, correct? Because I'm just saying that I want this particular quantity to become 1. So which means n by 2 to the power k is equal to 1, which means n is equal to 2 to the power k, which means k is equal to what? Log of n base 2, correct? So when k is equal to log of n base 2, the value of this guy will become 1. And then I know what is the value of t1. So then we can write at this point 2 to the power k. So instead of writing 2 to the power k, I know that the value of 2 to the power k is n. So I don't have to write 2 to the power k. We can write straight away n. N times t of 1 plus order of k is log of n base 2. And t of 1, okay, let's see, 2 to the power k. So this becomes n plus okay. Actually, there is a mistake in the recurrence relationship here. In this case, when there is an if then else, we are returning the value immediately. So in this case, by adding it up, we are kind of making the bounds become a little casual. So in this case, we should be taking, in one sense, because in both the branches is t of n by 2, right? So when we are putting this addition, it's actually magnifying the effect. So we should have done t of n by 2 plus order of 1. So this recurrence relationship is, I would say, too much flexible, or not flexible. It's just carrying too much of cushion here. So let's see what happens. So in this case, what the bound that we have come up with is n plus big theta of log of n, right? Now, clearly n is a more dominating factor. So this came out to be order of n, but this bound is not so tight. So let's rewrite the recurrence equation one more time. But this time, let's not put 2 times because it is in the mutually exclusive path. So let's put it in this way, and let's try to solve one more time. So in this case, what would we get? We will get t of n by 2 square plus order of 1 plus order of 1. Okay. And then t by So this I just substituted here. So again, t by 2 to the power 3 plus order of 1 plus order of 1 plus order of 1. So the same pattern follows. So this is 3 times, as you can see. So we can go down the same path. So t by n by 2 to the power k plus k, because this will become k times. So what do we get here? So if you have to make this one is equal to 1, the same condition is valid. So n equal to 2 to the power k, right? Or k is equal to log n to the base 2. So here we just simply substitute. So this becomes t of 1 plus k. K is what? Log of n base 2. So t of 1 we know is big theta of 1, and this becomes log of n base 2. We can write down big theta here instead of, because this is, let's say, big theta of k. So this is big theta of log of. So now between the two, log of n is a dominating factor. So this becomes big theta of log of n. So therefore t of n of binary search is log of n. Any question? I hope I was not too fast in explaining. Is it clear? Any question? Any step was not clear? So we saw, like, if we just add the if and the else branch, then especially when we are writing recurrence relationship, the bound becomes very loose. So the rule that we came up with in the fourth step, this is applicable when there is no recursion involved. So let's put that condition here. No recursion. If it is recursion, it's better to take the max of the two path, right? Because these are mutually exclusive path. Therefore, you need to consider the max of the two paths as opposed to adding them up. And we saw just the effect of that. When we were adding them up, we got a really, really loose sort of bound. And we ended up concluding that the complexity of this, the time complexity, is actually order of n or linear, right? But this is the complexity of the sequential search algorithm, the obvious sequential search algorithm. This is the complexity, because when you're going like step by step, element by element, this is the order of a sequential search. But when it comes to binary search, you are able to achieve log of n, and therefore it is much, much faster than sequential search. Any question? Are we good?
Like, I'm a bit confused. Just to recap, so the sequential search, right? The original equation that we wrote was t to the n equals 2 t to the n divided by 2 plus theta of 1.
I was multiplying by 2 here.
Yeah. So that's the loose one when we add the mutually exclusive.
This is the loose part. Yeah, this is what is making the bound loose.
But we're only thinking about the max.
Yes, because if you see here, we are only going to go to either this path or this path, right? I mean, when I was stating the rule 4, right? In the non-recursive cases, right, it's perfectly fine, because when you are adding them up, automatically the dominating term will tend to show up as dominating. So it does not matter. But in recurrence relationship, it matters. And therefore you should be taking max. You cannot make it additive. So the additive makes sense when there is no recursion. Otherwise, go for max. Or if you want to generalize it, I would say just go for max all the time.
Okay. Could you possibly give us like example problems and like solutions so that we can practice these?
Yeah, sure, absolutely. Yeah. There will be many more problems come. Don't worry. This you will see as we are learning more algorithms. This recurrence patterns will show up many more times later. this is just a beginning. But I hope like right now you saw these are the basic fundamental rules to apply when you are trying to find out the complexity of a given algorithm. So I just wanted to lay down some foundation so that from now onwards, for every algorithm that we look into, we should be looking for what is the time complexity of this. All right, so I think with that, I'm ready to switch gear at this point to talk about trees now.